That's a good reminder that this session is being recorded. If you're uncomfortable being on camera, please feel free to turn off your video. Just want to give everybody a heads up. So our approach as a nonprofit is really statewide. We're able to go around the state delivering different trainings from energy code to two-day high performance builder training. We're also in the K through 12 realm right now, delivering career presentations. And all of this is made possible by the generous support of the Department of Energy Resources and the Clean Energy Partnership. And we have additional funding from the Harold Alfond Foundation. I want to thank or welcome our two guest speakers today. We have Michael Pulaski and Vamshi Gooje. I've been working with Mike and Vamshi for the past few months on developing today's curriculum. They are experts in the field, each with over 20 years of experience in energy modeling as it relates to high performance building in the commercial sector. Really just grateful to have their expertise in the room. The flow of today's session is going to be me speaking about just giving a general overview of what the IECC is, so what we're looking at today. And then I'll pass it off to Mike and Vamshi, who will deliver best practices. At any point, feel free to load a question into the comments box. If I don't see it, Mike and Vamshi have their eyes on it, as does Dory. We will try to answer as we go if it's relevant to what we're looking at the moment. If not, we will set aside 5 to 10 minutes to cover any questions that we might have. I do tend to talk fast, but I definitely want to make sure that we get in all this good material. So I'm going to jump in right now to start talking about why we're here. I do love to give a little bit of context, right? When we're in person, I asked, building codes, do we think these are a modern nuisance? Some historical context shows us that no, not really. Building codes have been around for over 3,000 years. The earliest were written down in about 1750 BCE. At that point, they looked really, they were more about punitive measures, right? So on the code enforcement side, it kind of looked like if you were a builder and your structure collapsed on its occupants and the occupants died, you were also put to death. Luckily, things have moved from punitive to preventative. So over the past 3,000 years, we have been fine-tuning buildings as it relates to health and safety measures. Um, but really, what we're going to get in today is about energy codes. And we can see that energy codes are actually more of a modern code development. Um, Energy codes, attention started being brought to energy as early as the 1950s in the States. There was people began to default on their federally backed mortgages because they could not pay both their energy bills and their mortgages. We would assume that 75 years later that we don't have this problem, but we still do. People are still making that choice, to pay either their mortgage or their energy bills. Nationally, attention was brought again to energy in the 1970s with the US oil embargo. The oil embargo sent gas prices skyrocketing and the cost of petroleum products through the roof. So there was a real need to start having a mindset where we conserve energy in our built environment. So around the 1990s, our model energy codes start to take shape. And in 1998, the International Energy Conservation Code started to take shape, and that's what we're here to talk about today. So a very brief overview on what the IECC is. The IECC stands for International Energy Conservation Code. It's created and maintained by the International Code Council. The code book itself is built through a comprehensive stakeholder process. That means anyone can submit proposals for a change. It's then reviewed by a technical committee and approved by a public safety official. New editions, the IECC, are put out every 3 years. So how does all this work in Maine? MUBEC, Maine United Building and Energy Codes, adopts the ICC base codes. So that includes the International Energy Conservation Code, but it also includes things like the International Residential Code and the International Mechanical Code. MUBEC then takes those base codes and makes Maine specific revisions. UBEC also adopts reference standards. Pertinent to commercial code is ASHRAE 90.1, which is the energy standard for buildings except low-rise residential, and ASHRAE 62.1, ventilation acceptable indoor air quality. So it's the IECC base codes plus the Maine state amendments, plus these reference standards that equal kind of the code deck that Maine builders can work from. It's really important to point out that MUBEC is law everywhere in Maine. All new buildings constructed in Maine must comply with the IECC and other base codes, plus amendments. Um, the kind of confusing point is that there's language that says some towns with a population under 4,000 are not yet actively enforcing compliance, but that doesn't mean that builders or designers in those municipalities with 4,000 or less don't have to build to code. They absolutely do. MUBEC is law all across the state. Everyone has to build to these base codes plus amendment standards. So the question often arises, why do we build a code even when it's not enforced in a municipality? Again, just kind of harping on that point that MUBIC is still law, even if your town doesn't enforce it, right? So you might have a CEO in your town. If you're in a town under 4,000, they do not have to come and do the inspections, but you still need to build or design to that standard. Ignoring MUBEC is a violation of the law, and non-compliance, and this is the important part, can cause problems down the road. Builders can be held liable for issues that arise. One other point about MUBEC and its adoption process. They also have a stretch code, which means that in certain municipalities that opt to adopt the stretch code need to beat the base requirements by 15% over the code compliance. Right now in Maine, there's only 3 municipalities that are using the stretch code, and that is Portland, South Portland, and Freeport. So at this point, we know what our base codes are, and that we need to follow the base codes plus the Maine state amendments. And you also need to be aware of stretch code depending on where you're building or designing, because you might also have to meet that requirement. So where do we find these codes and information? The ICC base codes can be viewed on the IECC website for free. You can look at a PDF publication. And then the Maine specific amendments are currently housed on the Maine State Fire Marshal's website. It is moving to MOCA, Maine Office of Community Affairs soon, but last I checked, MOCA still links through to the Maine State Fire Marshal's website. All right, now getting into why we're here today. On April 7th of 2025, Maine switched from using the 2015 IECC to the 2021 IECC, and that looks like a 10% increase in energy savings over those two code publications. And for all the education and awareness that needs to be done when we change codes, we think, well, what is 10%? That doesn't seem like a lot. We have to zoom out a little bit to put in some context. That's a 40% increase in energy savings since 2006. So we're making big strides incrementally throughout each code update. We also know where codes are heading. This is a graph put out by the US Department of Energy. The red circle shows us where we are in 2021. And it's pointing down to that bottom of 2030 with the goal of net zero. This is why Passive House Maine, as a nonprofit, brings in people like Vamshi and Mike, who have been focused on energy modeling for the past 20 years and focused on high performance building, because we can see this is where codes are going. We're going towards high performance and passive house levels. So we know how to find our codes. We know which publications to look at. We know that we have to understand the Maine state amendments. We also have to be aware of where we are living, if the codes are being enforced or not. We still have to build to the codes. And then we also have to be aware of their stretch code. So now we have to understand, what is the commercial scope? What counts as a commercial building? By code standards, that's a non-residential building, 3 stories or more. Um, on the left, you'll see a 3-story mixed-use building, and the top 2 floors are designated residential, so you'd follow the residential provisions of the IECC. And since it's retail on the bottom, that would fall under commercial. But if you bumped that 3-story structure up to 4 stories, the entire structure would fall under commercial provisions of the IECC. So now we're going to jump into, okay, we know what our codes are, where to find them, we have all that information. How do we show that we've met this energy code? And that's called compliance. Compliance can be met in one of three ways, and it's at the discretion of the building owner or the designer. Um, and within the 2021 IECC, you can choose to use the prescriptive compliance option, the total building performance option, or ASHRAE 90.1. ASHRAE 90.1, until this publication of the IECC, used to just be a state-adopted reference standard, but now it's not just a reference, it's actually listed in the IECC as a compliance pathway. When we talk about how code changes between publications. We know that for 2021 IECC, the majority of the updates from the previous version, which would have been 2018, were increased in R values or decreased in U factors. And really, those increases or decreases were bringing the IECC into alignment with ASHRAE 90.1. ASHRAE uses a cost analysis to make sure that when they increase R value, that the payback period for the occupant or the building owner makes sense financially, that there's a return on investment on that increase of insulation. Um, I'm going to let Vamshi chime in here with additional energy efficient credits.
Yeah, thanks. Thanks, Erin. So one of the biggest changes in this particular ICC 2021 is the requirement to achieve additional energy efficiency credits. So it is not just meeting the R values and the efficiencies of mechanical systems or lighting power density, but you also have to get 10 additional points by choosing one of these things that you see on the screen. And these particular requirements are pushing beyond what the prescriptive requirements are. And one need to look what is your occupancy group type. So for example, a residential building has a different weightage for the points you can get for different credits, and business type could get different. So out of all these things, you need to achieve at least 10 energy efficiency points. So you have points for improving the heating efficiency for the heating system, cooling system, reducing lighting power density beyond what is prescribed, additional controls for the lighting. And for residential projects, they have specifically called out 3 of them. You see on the second column on the top 3. One is recovering or heat from the condensers, or having solar water heaters, instead of using fossil fuel based water heaters for the domestic hot water, using heat pumps, so on and so forth, and also pushing the air tightness further than what ICC prescribes. So these are some important pieces to keep in mind when you're looking at the prescriptive approach for your project.
Awesome. Thanks, Vamshi. The IECC, as noted, has 3 compliance pathway options, but the MUBEC has also adopted alternate pathways to show compliance that your building meets the energy standards, and that's the DOE Zero Energy Ready Home Certificate, or the Passive House certification, either by PHI or PHIUS, PHI being the Passive House Institute, or PHIUS being the U.S. version of PHI. All right, now we're going to get into kind of the nuts and bolts of the compliance pathway options. We're going to chat first about prescriptive compliance. Prescriptive compliance in commercial can be met one of three ways. It can be met by following the R value table. It could be met by following the U, C, or F factor table, or it can be met by following the component performance alternative. So you're in prescriptive compliance, you choose one of those pathways, say you choose R value and you go by the R value table. You also have mandatory requirements regardless of which of those pathways you choose. Um, so you have to meet the R value table and then those three additional mandatory requirements, plus those energy efficiency package options are credits that Vamshi just outlined. So you have to do all those things to follow and show compliance in the prescriptive way. Prescriptive is the most, you don't have any trade-off or flexibility, particularly when you're following the R value or U factor table. You start to see some trade-off when you go with component performance, meaning that, the R value table is going to list every component of your building, but from foundation to roof, and list the R value. Um, Once you get into energy modeling, if you say put in better windows and doors, you might be able to take reductions elsewhere. So energy modeling can be viewed a little bit as a cost savings or at least optimizing your insulation instead of just following the prescriptive checklist of R values and insulation values to meet. I'm going to also kick this one off to Vamshi, right? Or is it Mike? And this
Yeah,
is just
I can
cool.
take that. So as Erin showed earlier, there are two ways to meet the envelope performance requirements. One is R value, U factor, and the last one, this one. So the other two options, you must meet those R values or U factors. With this one, it gives you a little bit of flexibility within the envelope components only. So you cannot do a trade-off outside the envelope components. So what it does is if you are unable to hit certain R values for your wall systems, for example, for whatever practical reasons you cannot insulate beyond the prescribed R values, then you can compensate for that on the roof. You could add additional inch of insulation or 2 inches, whatever that case might be. So what it does is it takes the U factors of your walls, roofs, windows, slab on grade, and all your envelope components where your heat losses are through. And for each of those components, you multiply the area of that surface, and then your design case overall should be less than that if you're using U factors, right? So that would help the design teams where you are, where you don't see much benefit in insulating the walls. For example, you have very large roof area, and you may not get much out of insulating in the walls as much you would get from the roof. So you may want to move some of that R value to the roof instead of in the walls. So this particular compliance path is very useful in those circumstances and gives the flexibility for design teams a little bit more.
I could just chime in for one other opportunity here that I see is to try to figure out how to cost optimize your envelope. This allows you, as Vamshi was saying, to sort of put more insulation or better performance in certain components and less in others. And so one opportunity is if you're having better windows, better performing windows, which is really important in our environment, you might be able to reduce the insulation on the wall systems or the roof systems in order to accommodate that, and then find the most efficient way to achieve your performance. So it gives you that flexibility when you're with a very simple tool, just doing a spreadsheet calculation of the U value of that product and the area that's in the code versus the U product in the area of what you're proposing.
I'm also going to let Vamshi and Mike handle the next two compliance options. We have total building performance up next, and then after that, ASHRAE 90.1. Vamshi, do you want to take?
Yeah.
Okay.
Yeah. So this is the other option that Erin showed earlier. This is one option where you use energy model to show that your proposed design is performing at or below the energy code. Um, and one of the advantages of this one is, as I mentioned earlier, for the component performance for showing compliance with just the envelope piece, you are stuck with trade-offs within the envelope pieces. Whereas in total building performance, you can do trade-off between different trades or disciplines. Like you may have really efficient lighting systems, really good lighting controls, and that could, contribute to the overall performance of the building. So what is really required in this particular approach or pathway is you create a baseline energy model, which corresponds to your standard reference design case, reference case, which is your IECC 2021. So you're building your envelope systems as per the R values or U factors in IECC 2021, your lighting part density as per IEC 2021, your mechanical system efficiencies as per IECC 21, so on and so forth. And then you create another model which aligns with your proposed design, and you build that model, develop that model, and the target is we need to be 20% less than your reference standard energy model. So this is one of the, again, big changes in the energy codes that have happened since the previous one. Initially, it used to be you just meet your standard reference case. So even if you are like 0.1%, you would meet the code. But in this particular energy code, they have made the target 80% less or 20% savings over your baseline energy code. So one of the reasons is also because you're able to do trade-offs between various disciplines. This is making sure the design teams are not using the energy model as a way to trick with the compliance of the energy code. So you're in a way pushed into making optimized decisions for optimized envelope and optimized lighting system, optimized mechanical system, so on and so forth. So they're by making this 20% target as a requirement, they are pushing in all rounds, but still giving you the flexibility to invest in the right systems for the project. And one more thing is we cannot in any of these options, especially in the performance pathway, we cannot use on-site renewable energy to show that 20% reduction. You can show only maximum of 5% reduction using the on-site renewable energies. So that is not to say that you cannot have more than 5% on the site, but only 5% of that is going to be accounted when you're calculating your proposed design savings against the baseline. And if we go to the next slide,
Vamshi, hold on one second there. One of the other main points that we want to make here with this change in the code is that what this does is it makes it really hard and difficult to do heavily glazed buildings now. So the prescriptive path, once you're over 40% glazing in a building, you have to do this whole total building performance model. So if you wanted a building that's 50% glazed, you can't use the prescriptive requirements. You have to use this modeling approach. And previously, all you had to do was basically install some heat pumps, maybe make a few more pieces of equipment, lighting more efficient, and you'd be able to balance out the code and meet code. But now you have to be 20% better than the base code. And for reference, when we were doing design of buildings, the getting to 30% below code is basically hitting passive house level. So now you have to be at 20% just to use this performance method, which makes it very difficult. And one example of a project that many of you maybe see or familiar with as you drive by 295 is the new Rue Institute building. So that building we modeled previously in our previous company, and that was achieving 30% better than ASHRAE 90.1 2019, which is the current base code. But it has 60% glazing, all high performance triple glazed windows, 80 geothermal wells there, to help balance out on the efficiency side, high performance heat pumps in addition to that, for the load. So you have to do a lot in order to make up for a more heavily glazed building.
Thanks, guys. Moving to the last compliance pathway option, Vamshi, I'll kick it over to you.
Yeah. So ASHRAE 90.1 and IECC 2021, they are a little bit staggered or have been staggered historically, but now they're actually trying to align with each other. And there always been cross-reference in IECC 2021 to ASHRAE 90.1 sections. So the other alternative method for showing compliance is ASHRAE 90.1 Appendix G or Section 11 for energy modeling. Or you could also use prescriptive, which would be pretty similar to ICC 2021. The one important difference in ISO 90.1 is they have clearly described the modeling methodology. So it's very well detailed out. And there are two different approaches, even for energy modeling, that I was earlier talking about, which is Section 11, energy cost budget, and performance based pathway, which is the Appendix G.
Now we're moving kind of out of compliance pathway options, but how you can also show compliance. And we really love to promote res check for residential energy code compliance, and then com check for commercial buildings. Com check really simplifies energy codes, and particularly in showing compliance. It's a free online software. Anybody can use it. Anybody can access it. It's web-based. When you open up ComCheck, this is what the landing page looks like. You do need to know a few key details. What is your energy code? Where are you building? You need to know project details, building type and size. You need to know your area takeoffs for your envelope. So roof, walls, floors, foundations. What are the R values or insulation values? You need to know your lighting information and mechanical system details and your service water heating information. But when you have all that in hand, you can sit down and use ComCheck. And once you have all the information put in, it will show you very clearly if you met the energy conservation code. It really takes out the guesswork of have I complied with the code or not, less referencing the code book itself or reference standards. And new in the last few months is that ComCheck and ResCheck both account for main specific amendments. So if you plug in your state and your zip code, it will automatically kind of load in the main specific amendments so when you see if you comply, you know that you're not only complying with the base codes, but you're also complying with the main state amendments. It can get a little confusing because the drop downs for both ResCheck and ComCheck do show different states, maybe North Carolina or California. But ComCheck and ResCheck are moving away from that model of having the name of the state and just using the zip code to have the state-specific amendments built in. We always suggest that people go home and give this a shot. ComCheck is obviously a little bit more data to input, but ResCheck is a similar program. And if you can just have a sample project, load it in, and then check compliance. When you do that, you can also download the compliance report, which has a lot of detailed information, particularly for code enforcement. It's a very detailed checklist of inspections. It prints out a permanent energy certificate, so it shows what compliance pathway you're using, what your R values are. It's a very handy tool, and particularly in municipalities that are using stretch code, where you have to show that 15% better. One of the easiest ways to do it yourself is to use ResCheck or ComCheck. because if you pass code or you exceeded compliance, it's going to give you that percentage in which you exceeded compliance. So a really great tool that's free and available to everybody. Existing building scope. So we always have questions about, I'm not building a new commercial building, I'm not building a new residential house, but I'm working on an existing structure, and what does that mean for me as far as meeting the IECC? And it really depends on the scope of work. Additions, the new addition must comply fully with the 2021 IECC, but largely, and that is with any scope of work, the parts that are untouched or unchanged in the building do not need to be brought up to meet compliance of the 2021 IECC. If we're doing something like changing an unconditioned space to conditioned space, typically that whole entire space needs to meet the new energy standards. Mike or Vamshi, do you have any other additions for existing building scope? No? All set? Okay.
I think you covered it.
All
Yeah.
right. And now I'm going to stop sharing my screen. I'm going to let Vamshi take over with his screen, and Vamshi and Mike are going to go through our best practices and how we meet energy code.
Great. Thanks. Let me see.
Give you a minute.
You can see my screen, right?
Yes.
All right. So we wanted to highlight a couple of things, mainly focus on things that have changed significantly since previous energy codes. And so we can think about specifically 2 to 3 areas where there's been a major shift. The first one is addressing the thermal bridging. And then the second one is the air tightness of envelope. And then third one we talked about earlier, like additional energy efficiency credits. So we're not going to get into details of that. But these 2 areas are very important. The reason is, once they are built, it's very hard to go back and fix them. So we want to highlight some of the, case studies or best practices in this area and, how it can be achieved. And one of the things also to highlight is previously the intent was right. It was expected, the design teams who are paying attention to thermal breaks in the project, but there was no verification process. But now, some of those requirements are getting into the code. So what we are going to go through in the next few slides is the continuity of insulation, air barrier system, and we'll also go in the sequence of going from the top of the building to the foundation of the building. And as you can just read out here, these are some of the weak points in the envelope that we have come across in our practice, where there is tremendous amount of heat losses to these areas. And no matter how well you're insulated, if these thermal bridges are not addressed, then overall your envelope is not going to perform as well as it's supposed to. So
The code,
yeah,
before you start going into that, I mean, one thing just to be crystal clear here is that the code now requires you to do air barrier testing and performance of the envelope, and so their code requires you to meet a value of 0.4 CFM per square foot of air leakage at 75 pascals for the whole building. And so from a commercial standpoint, this is brand new to the commercial world, and is not something that's typically done. And so now it's required, and there's a hard ceiling of what you have to meet in order to achieve it. So we want to sort of take the time here to give a couple examples of how, some of these air barrier details and where it's important and what to look for, where some common leaks can occur. but really to sort of just raise the level of awareness that this is now important. It's required. You have to test at the end of your project, and it's a pass-fail situation. And if you fail, then you've got to go back and do the remediation and figure out, troubleshoot where those problems are. So we'll go through some of these details. We have a couple of best practices that we've learned over the years. And just to sort of put in full context here, for the last 20 years, Vamshi and I have been working on high performance projects throughout the state, throughout New England, and across the country as well, looking at super high performance lead projects, passive house buildings at the commercial level, living building challenge, net zero energy projects, particularly schools, and other high performance systems around the state and throughout New England. So we have one example that we're going to share with you today that goes through. It's a passive house dorm project in Massachusetts that will have some of the details to kind of walk you through that building.
It's Mike. So we'll start with the parapet detail. And as you can just read on the slide, it has potential to reduce the effective R value of your system by 60%. That's a lot. So that's how much you're wasting the money by investing in an envelope if you're not addressing this one. And most of these areas that we're going to run through are transition details. It's not necessarily like, just one what you call a homogeneous system type. So in the parapet, we like to see no parapet, so the detail is better. There's a continuity of insulation and also air barrier. So in all these diagrams, if you see the red dotted lines, that corresponds to air barrier, and the yellow is the insulation. So you can see in the middle diagram that there is continuous insulation and also air barrier system. And the issue with having parapet is if you have short parapet, you can still manage to get a pretty decent detail. But as your parapet height increases, you have potential for some of the warm and humid air from the inside escaping into that area and potentially causing some condensation issues. So it's best to avoid it. If you can avoid it, consider short parapet walls, and then think about how you eliminate the thermal bridges by having continuous insulation and air barrier. And the second piece that you see here is definitely more cost-effective way to do it. But there are also in circumstances where you cannot actually wrap the insulation around the parapet for whatever reason, then there are some structural thermal pads available, Fabrica, Armatherm, and just a couple manufacturers who do them. Those can also be used. And this is in that little brown brick looking thing between the parapet wall and the slab that you see on the third diagram. And here's an example that Mike is gonna quickly walk through.
Yeah, so this is the project at a high level. It's a 45,000 square foot new dormitory for Wheaton College called Pine Hall. As I mentioned previously, it's a Passive House certified project. At the time, one of the largest dorms certified, and in New England. And this is from a construction type. It's a typical commercial construction type with it's a steel frame building with concrete plank floors, and metal studs on the exterior wall. And it has the project used the high performance. It was an Intus brand window for the windows, but from a detailing standpoint, the detail here on the parapet is up on the left, which looks very similar to the middle detail that we just saw, where you've got some continuous insulation that goes on both sides of the parapet wall and as well across the top. Even though it's relatively small, it's enough to cap off the top. And then you can see the air barrier there is in red as it goes all the way around the entire up the entire parapet wall and then come back and around on the outside.
And the next detail is, there are two types of thermal bridges that I should have actually started with. One is the linear thermal bridge, which means it's very continuous. It goes across the entire axis of a particular surface. And the other one is the point thermal bridges. So point thermal bridges, you can think about all fasteners used to secure the sheathing to the structure, right? So you don't have continuous thermal bridges there, but only point thermal bridges. So one of that such point thermal bridge is the roof screens or dunnage that you have on the roof. And similarly, they have potential for 15 to 20% um, reduction in R value when we run heat loss, heat transfer analysis, right? It depends on how many point thermal bridges you have, but that's a rough average of how much heat you can lose through these details. Similar to other details, again, we have in this case the thermal brake pads that are structurally robust as well. We cannot always use standard insulation materials in these cases. And because they're not extensive area, these might be a good applications for using these structural thermal pads. So here you have a continuous air barrier on the roof, and that brown little thing between the plates, actually, you can see on the right side in a real world case as well. And here's a similar detail.
And this is the detail from the Wheaton College project. And this you have structural steel tubing coming up out of the deck, and you can see the Fabrica pad there called out. Just creates a separation between the warm concrete block and the steel pad. And one of the primary reasons that we're showing you these thermal details is that this can be an issue from condensation. And so if you have this cold steel plate coming in and connecting with warm air on the warm slab, water can condense on there, create condensation, and have problems, and that can occur in any of these situations. So having these thermal brake pads and our other thermal brake details is critical to eliminating that risk for condensation. Similar detail for elevator overrun here. In this case, it's just looking at this is a detail that exists on every commercial project, and you just have to make sure that you're detailing it and paying attention to the air barrier on it. There's less on the thermal bridging here, but more just the fact that you have to follow the dash line around the outside of the wall system that comes up over the top of the roof, and then comes all the way into terminating at the curb there.
Here's the balcony details. If you're in Portland area, you see these new high-rise residential buildings having balconies, which we never used to have traditionally. But these are, again, radiating heat from inside to the outside significantly. And these are, again, linear thermal bridges, not necessarily point thermal bridges. And you can see a thermal break block between the cantilevered portion there and the structure. So this is one way to eliminate that heat losses through balconies. And it's very important because otherwise they're like radiating heat to the atmosphere, literally. And the other continuous or linear or point bridges that could happen quite often is when you're attaching your rain screen to your system. You either have like Z channels, Z girds, or hat channels, or whatnot, the way you design it. If these are not decoupled from the structure, they can also lose up to 65% of heat or loss of R value in the envelope. And just to kind of highlight how critical this is when you're using prescriptive approach for compliance, you know, if you don't address these small details, you may have to end up insulating significantly, which makes it almost impractical to meet your energy code. So these are very important, and especially in the latest code. It used to be, but there was no verification, and now they want to make sure that your thermal bridges are accounted when you document your U factors in your drawings and specifications. So there are Z-girts, there are some fiberglass-based spacers, and so on and so forth to eliminate thermal bridges. And to the point, also, it's critical to think about moving as much insulation as possible to the exterior so that you have that continuous insulation rather than putting between the stud walls, because again, the studs are thermal bridges. We cannot have 8 inches of insulation within the stud cavity and expect we are getting really 8 inches worth of R value out of it. We're going to only get less than half of that without continuous insulation. And the communities or the municipalities not in Maine, but south of Maine, especially in Massachusetts, that have adopted the latest energy codes, they have stretch energy codes. We've noticed, the designers are starting to figure out how to do continuous insulation, only continuous insulation on their projects. So once they have that detail figured out, they continue to use that as a template for the other projects as well. And shelf angles, again, a continuous when you have masonry that you'll see in a lot of buildings in Maine as well, especially in K through 12. They have some face brick facades, and then also you have similar heat loss potential through the envelope. So it's good to look at thermal break pads where your shelf angles are connected to your structure. You also have the fiberglass reinforced shelf angles as well, which have slightly better R value.
So
And
this
this
is
is an example.
this is a quick detail from Wheaton, and you can see that outside of the wall system, there's actually about 5 inches of mineral wool there, and there were some Z-girts in between there that then connect to the angle that holds up the brick. So that's the detail that we ended up working out through Wheaton, but the key piece here is this 5 inches of mineral wool. And then on this project, as kind of a belts and suspenders approach, they ended up putting in closed cell foam on the inside in the stud cavity to help seal up any potential penetrations that come through that exterior wall. I will also just say too, if you have any questions for us, please feel free to drop them in the chat. I know we have just about 10 minutes left on this, and we'll go through the last section here, but we'll try to address any questions if people have them.
And this is another critical area to look at the thermal bridging, is the fenestration, your glazing system, how they are connected to the wall, especially at thermal window buck. That is the area where you can't usually get the continuous insulation on the outside, as shown on the left side of the slide deck here. But there are options where you can potentially use thermal buck, which are actually insulated materials, so you do not lose as much heat through them. Or there are alternative ways to detail it so that you have the window glazing right, along the exterior insulation, so that you're not going inside, in which case you will have heat loss like this through the frame and everything. And frame is the weakest point in the whole window frame too. And it could also potentially cause condensation when you don't take into account these heat losses.
And this is just the detail for the Wheaton College. And in this case, what we decided to do was bring the insulation up to the sill and try to create a small thermal break there between the sill and the window assembly, both on the top and the bottom.
And the last detail to pay attention to is the foundation. Typically, we'd like to see the insulation going all the way from the wall, the continuous insulation, to the top of the footing. If you have below grade, conditioned spaces, it becomes obviously even more critical to continue that insulation to the top of the footing. And otherwise, you also lose a lot of heat through the slab edge. And again, here there are easier way to do, which is using the proper detail to continue the insulation down the grade, or you could also use the thermal blocks from similar manufacturers we earlier mentioned.
And this is again the detail from Wheaton College. We're down at the footing, and you can see as Vamshi noted, the insulation goes continuous all the way down to the bottom of the footing. And then just to the left of the insulation is actually a CMU wall that then comes up to a piece of granite that then supports the brick. So that's how the brick ends up being supported from the ground, is all the way down to the footing. And that way you can have this continuous insulation that comes all the way down. The other piece to note here is at the slab edge. So a typical slab edge detail to the bottom right there, Vamshi, is has a piece of insulation, usually about an inch or so, that separates the slab edge from the stem wall, and then you can see the insulation underneath it as well, underneath the slab.
Okay, so moving on to air tightness. One of the biggest challenges that you'll come across on commercial sector is the scale of the project, right? The blow door test has historically been for single family homes, smaller scale projects. But how do you test infiltration in large scale commercial buildings? As we mentioned, it moved from intent to verification. So you need to submit blow door test results for your projects to the code officials to ensure that you have met, the 0.4 CFM per square foot at 75 pascals. Here's one example of how we kind of evaluated or looked into different options, how we can do on large scale buildings. This is coming out of a 250,000 square feet commercial building. We looked at potentially doing an in situ mock-up so that it doesn't impact the schedule, because that's going to be one of the biggest challenges, to get the air infiltration integrated into the construction schedule. If that is not possible, then the other option is to do on-site mock-up, like 8 to 12 feet of mock-up section, so that different trades can coordinate who comes first, who comes right after it. And it is very important to have one primary air barrier lead, so that they can, translate the coordination pieces and how different trades are going to work in tandem. And then the other thing is also you can do compartmentalization and test sections of the buildings, which can be very easily blocked off from the rest of the building. And this is also allowed by the energy code. The only thing you need to do is do the weighted average of these different sections that you have tested and come up with the average of that, weighted average of the overall building air tightness. And if it's a commercial residential, there are some provisions for, if it is less than 8 units, you have to test all the units. And if it is greater than 8 units, you need to test a minimum of 7 and then 20% of rest of the building. And there are a lot of things to cover here. It's a topic in itself, but we're going to just give you an overview of what are the things to pay attention to. Mike has earlier mentioned about what is the standard is zero point 0.4 CFM per square foot. It's a pretty good airtight building for commercial projects. For residential projects, slightly below that. As I mentioned, there's a primary air barrier lead, um, and this has to be redlined in the drawings and submitted for code officials to review it to make sure they are continuous. There are no gaps or breaks in the air barrier. And some of the design phase and construction best practices we'll walk through quickly here. Mike, you want to jump on this one?
Yeah, so just to highlight a couple that you see on the screen here. One is to just pick a particular air barrier type and stay consistent throughout. Don't try to um, change types throughout. You can have sort of products that may not work well together. Over time, they may separate. The transitions, we hit up all those detailed transitions. That's why we went through each of those parapet details down to the foundation detail. That's where your leakages are likely to occur, as well as around the windows. So that's where you want to pay most particular attention. There's also issues around to pay attention to the curtain wall interface. Using compartmentalization were helpful as well. And then look at managing how you manage your pressure during design, about pressurizing vestibules and certain spaces within the building. From a design standpoint, the spec language, you want to have your submittals. You're going to have submittals to review, to look at this to make sure it's acceptable with your design. Mock-ups are also very important and highly recommended. We can do in situ, sort of in design, in progress mock-ups, as well as standalone mock-ups, but figuring out a game plan ahead of time is really critical, and having the trades come around and look at those mock-ups and work through the installation is really important. On the contractor side, having somebody is basically, you need an enhanced quality control program here. And once you do this once, we see from contractors that it becomes part of your standard progress. And it's just one more thing that you have to pay attention to. And somebody on site has to be dedicated to managing the air barrier and making sure there aren't additional penetrations being made, or if there are, that those are sealed up. The last thing is interim testing in the construction phase, and you can keep it on this one. But we really recommend about halfway through construction, before drywall gets put on, that you come in and do a blower door test, and test the building, do smoke testing, see where the leakages are. There always are some that it's much easier to fill those leaks before you have drywall on and before you start putting finishes on. So that's critical. Also, during construction, a couple of best practices that we've seen is getting your subs together ahead of time and having a pre-install meeting to walk through these requirements, because they are new on a lot of projects. So to make sure, one, that they know about them, and two, you talk through sequencing or where the trades overlap in producing those air barriers. Again, managing the edge and the shafts and the stairs and the MEP disciplines where your penetrations are. This is something that MEP contractors aren't typically used to sealing up their punctures very well. So this is something that needs to be elevated. Overhead doors, if you have overhead doors within your system, those are often also leaky. So making sure that you've got high performance gaskets spec'd on those. And as you're going through, make sure you certainly want to document any fixes that occur, and make sure you take a lot of photos, because once you cover up the walls, you don't know what's behind them, and that'll save time later on if you need to fix something.
All right. We are coming up on time. We do have a few more slides on commissioning. So I think what we could do is we can send out these last couple of slides on commissioning with a detailed email. But I do like to be cognizant of everybody's time. So we are going to end the session here. I want to thank Vamshi and Mike for their time and dedication to helping us launch our commercial iteration of our code training. Thanks to Dory, our program director, for helping us moderate this. And thanks again to the Department of Energy Resources for making all of our trainings possible. I appreciate everybody's time. If you have any follow-up questions, I am here as a resource, and you'll have slides and an outline and an explanation of commissioning in your inbox shortly. All right, thanks everybody.